So I have been talking about two subjects, adding numbers and shuffling cards. And yesterday I allowed myself to talk about, or you allowed me to talk about adding numbers. You might think it was hard to talk for an hour and a half or however long I talked about adding numbers, but I managed and you managed. And today I'm going to talk more about shuffling cards. But the thing to talk about is another way of thinking about shuffling cards, which has to do with geometry. And I'm going to start with that. But if you're a magic guy or here for shuffling, shuffling's coming, but you won't recognize it for a few minutes. So the object of study is let H1, H2 up to HK be affine hyperplanes. In RD. So, a subspace, a plane is a codimension 1 subspace, and then an affine hyperplane is the shift of that. So, for example, when D is 2, it might be that I have some lines. These are supposed to maybe go through that point. They don't have to be any affine plane. Hyperplanes. So, these are these are 1, 2, 3, 4 lines in R2. And a collection of hyperplanes slices RD up into chambers which are points not on any of the hyperplanes. So I think in this picture there are 10 chambers. 1, 2, 3, 4, 5, 6, 7, 8, who knows, 9, 10. It's easy to miscount, but I think that there are 10 chambers. This, this goes on forever, right? These are lines. And once and for all, it's not crucial, but I'll use it. We fix at the start a positive and a negative sign for each side of each hyperplane. So maybe for this hyperplane, this is the positive part and that's the negative part. So each hyperplane, its complement is divided into 2 parts and called 1 plus and 1 minus. It doesn't matter how you label them, but fix it at the beginning and that's good. So those are the chambers of a hyperplane arrangement, and I'll be calling those script C, the set of chambers, and I'll be calling the set of hyperplanes, the arrangement, script A. And then there's the notion of faces, definition. A face of an arrangement is on some HI and one side or another of others. So that's a little vague, but it's easy to say others. So, for example, this is a face. That is, this face is on this hyperplane. The face could be on several hyperplanes, and and then this face is on the positive side of this, and the negative side of this, and on the positive side of this, and so. Is that okay? That is the notion of a face of a hyperplane. So points where the hyperplanes, points can be faces. The hyperplanes are also called faces, and there's the empty face, and I have the collection of faces. Let script F be the all faces. So that's some finite set. And the notion that's crucial is the notion of the projection of a hyperplane, of a chamber on a face. So I'll put it here. Definition, the projection of C on F, the projection of the chamber C on the face F is, so that's, I'm defining that now, is the closest chamber adjacent to F. Here close means you cross the fewest number of hyperplanes in going from C to S. So let's bring this down for a second. So the projection of this chamber on this face is this C prime, because to get to C prime, well, you can go 1, 2, 3, right? And the other chamber, which is adjacent to F, if this is F here, the other chamber that's adjacent to F is this part, and you'll see that however you go, it takes you more than 3 steps. So this is uniquely defined. It's called Letit's projection after Jacques Tits, and I mean, I can define it, you know, a lot of other ways, and in symbols various ways, but I hope it's clear what the projection of a chamber on a face is. So the projection of a chamber on a face is another chamber. So that's the ingredient. Those are the ingredients. I'm in Euclidean D space. I have a bunch of affine hyperplanes. I have that defines some chambers and some faces, and there's this notion of projection. And the final thing I need, instead of getting rock and roll, I'm going to get ready to walk. But I need to choose face weights. Let WF, F contained in F is the set of all faces, be WF are non-negative, they could be 0, and the sum of all of them is 1. F and F. So these are face weights, and I have to specify them, okay? And now I can now have a random process, and it goes as follows. Start at some chamber. There I am on some chamber. Pick a face, this one. Move to the chamber adjacent to that face. There's a unique such place. Just keep going. Let's just pick another face from the face weights, independent, identically distributed, and then move to that chamber. Is that okay with everybody? It's just, you know, just that defines, I'll write it down, that defines a Markov chain. K of C prime, the chance of moving from C to C prime is the sum of WF overall F, such that the projection of C onto F is equal to C prime. You know, the chance of moving from C to C prime, you have to pick a face, which is, you know, for which C prime is the closest face to C. So that's, and well, there are going to be many examples. There are going to be many examples coming of these walks. And right now you might be thinking, wait a second, no, I'm in some funny subjects. This has to do with shuffling cards. And if you're a probabilist, it maybe seems even stranger. Okay, so let me do some examples. So you see it's not as crazy as it seems when you first meet it. So let's take the Boolean arrangement. That is where the ith hyperplane is just what you think. It's the ith coordinate plane. It's the set of all x such that xi is 0. So, if I was this way, there are two hyperplanes, just the usual coordinate hyperplanes, and this might be plus plus, this might be plus minus, this might be minus minus, and this is minus plus. There are actually 9 faces. Because this midpoint is a face, there are these 4 half lines that are faces, there are the 4 chambers, and then there's the empty face or everything. I mean, but there are 9 faces, the usual way we reckon it. And so that's called the Boolean arrangement. And the number of hyperplanes, of course, is D. This is X and RD. How many chambers are there? Well, it's the coordinate orthants, the size of the number of chambers is 2 to the D, of course. And how many faces are there? Well, it's 3 to the D, because you can specify a face by a sequence of length D, where the ith coordinate is 0 plus or minus as you're on that hyperplane or on the positive side or on the negative side. And you can do those arbitrarily, and any such choice gives you a face. And so when D is 2, there are 9 faces, and it's okay. And then I have to explain the projection operator. What's the projection of a chamber on a face? So projection so I'll do it by example, but I hope it's clear. If the face is, say, plus 0, 0, minus, and if the chamber is, plus, minus, plus, minus, okay. The chamber, it shouldn't be scriptsy. Okay, so the chamber is, you're not on any hyperplanes, and the face, you're allowed to be on a few of them. The projection is if f, the ith coordinate, is not equal to 0, this rules. You keep that core. If it's plus or minus, you just keep it that way. And if fi is equal to 0, then C rules. So the projection of this on this plus stays there. Here it's a 0, so it becomes it would become plus minus, I think, if I did it right. Here, this has a non-zero coordinate. Here, you use the coordinate from C. Here, you use the coordinate from C. And here, it has a non-zero coordinate. Okay, that's the projection is the closest chamber to the face. And if you think about it geometrically, that's what it becomes. But that's so. Let me give an example of this Markov chain. So the random walk we're talking about, the Markov chain. I don't know why I do that, but the Markov chain here is on, I'm going to call it a C2 to the D, a set of all binary D tuples. I'm calling them plus or minus or 0 and 1, but that's the labels of the chambers. And suppose I choose face weights WF to be equal to 1 over 2d if f is equal to all zeros except in the ith place when it's plus or minus 1, and then all zeros otherwise, and then 0 otherwise. So there are d possible places, okay? My face weights are constant 1 over 2d if the face is got a plus or minus 1 in one coordinate, 0 every place. So what does my walk become? What does the walk become? If I'm at a binary d tuple, I pick a coordinate at random, and I change it to plus or minus 1 by flipping a coin. That's what this becomes, right? That is, I project onto that face, and so it's all 0. So I only change one coordinate, and then I change it to whatever this coordinate is. So the walk Markov chain becomes nearest neighbor walk on the hypercube. And that is and this is minus, 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 minus. This is plus, 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 plus. And, the neighbors are, you change one of the coordinates to the opposite, except that it has holding a half. That is, half the time, I'm going to pick the ith coordinate, and it's plus, and I'm going to replace it with a plus. Well, so if you're just looking from the outside, you think I did nothing. Right, so it's nearest neighbor random with holding a half, just not. Okay, so that's just a very simple example of these hyperplane walks. But this is a famous example, and let me tell you the story of it. It's called the Ehrenfest-Ern. Around 1860, Boltzmann floated statistical mechanics, and Maxwell picked it up, and then everybody picked it up, and people started computing things about the real world by putting probability distributions on configuration spaces. And it's been very successful from then to now. The mechanics is very complicated, impossible to solve. Avogadro's number of differential equations, and so you put a probability distribution and then compute certain probabilities, and the statistical mechanics. And Boltzmann became a great hero. And okay. Around 1890, so Boltzmann claimed that with entropy increases. That's a famous claim of Boltzmann, and he proved it the way physicists prove things. And no, but I mean, he had a proof. And at the same time, around 1890, Poincaré proved his recurrence theorem. So let me say it in English. So a typical example is you have n particles in a box, all on the left-hand side, and there's a membrane, right? And so I have n particles on the left-hand side of the box, and then they'll diffuse through the membrane, and it's clear, intuitively clear, that after a while the particles will be all over the place, right? Of course, right? So all the particles in the left-hand part of the box, that's small entropy. Random, they're all over the place, that's big entropy. And as time goes on, entropy increases, and of course it's true experimentally. But Poincaré proved that if you wait long enough, all the particles will be back in the left-hand part of the box. And that's what Poincaré recurrence theorem says. And you might say, yeah, who cares? Well, people cared. This is called the Zermelo paradox, and it really bothered people. It bothered people enough so that the physics and chemistry community turned against Boltzmann, and the two chemical societies and a physics society had each separate meetings, and they voted that statistical mechanics was not allowed to be published in their journals. And no, because at the time people didn't know that there were atoms. They didn't know that there were atoms. And so Boltzmann was postulating all of these unobservable parameters. And if you give me 10 to the 23rd, parameters, I can fit a lot of stuff, right? So sorry, but Boltzmann killed himself. So if you're smiling and think, aha, it wasn't aha. Boltzmann killed himself. It was a big deal. And then Einstein discovered atoms. I mean, proved to the satisfaction of the physics community that there really were atoms, 1906. And the Ehrenfests, Paul and Titania Ehrenfest, wrote an article around 1910 trying to explain the Zermelo paradox. And they said, look, forget about gas molecules and Newton's equations. Let's just take a simple case. Suppose that there's two urns, like the left and the right half parts of the box. Suppose that there are two urns, and you have n particles, say n is 10. You have n particles in the left-hand urn. Each time the dynamics are, you take a particle at random and you move it to the other urn. Okay, so that's a sort of toy model, toy squared model, a toy cube model of this dynamics, of gas dynamics, right? Now, obviously, if there are 10 particles, well, first of all, if there are 100 particles, I mean, they get all messed up. I mean, they do. But it's also obvious that infinitely often they'll be back in the left-hand urn. Of course they will be. Suppose there are 3 particles. And that's this process, exactly this process, but in a slightly different coding. I talked to you about two urns, but to each particle, assign a binary vector of length n as it's in, how do I do this? How do I do it? Each particle, how do I do this? According as, how do I do this? How do I do this? How do I go from to a walk on the hypercube? So I have a configuration. That is, the particles are labeled 1 up to n, and I write a plus if they're in the left and a minus if they're in the right. Okay, so that assigns to each configuration a binary vector of length n, and then pick a particle at random, move it to the other urn. That's exactly nearest neighbor walk on the hypercube. And this Markov chain is exactly the Boltzmann, the Ehrenfest Markov chain. So if you're thinking, oh, that's silly, right? It's not so silly. The analysis that I'm going to tell you that follows from what we do gives the first sharp answers. There's a phase transition, there's interesting analysis, there's interesting math. It'll come from these tools. So that's just the example 0, but there's 100 examples, and they all have pretty interesting stories. Let me give one other example for the Boolean arrangement, so example, I'm going to pick a simple graph, and you could make it any graph, but I'm going to 1, 2, up to n. I have a path of length n, and label the vertices plus or minus. Right, so the configuration space is the set of all binary n-tuples, and the dynamics are pick an edge at random, and change to plus plus or minus minus with probability 1/2. So you could think about these, you could make it a general graph, and there's an edge between two people if they know each other, and there's plus if they're Democrats, and there's a minus if they're Republicans. Okay, you can make up lots of stories, and all of a sudden, you know, YP and I decide, yeah, we're going to vote next time, or whatever it is, and we both become pluses. Or, this is idiotic, we're not going to vote next time. So that's this process. And you could think through, because I've given you all the ingredients you need, that's a very special case of Boolean arrangements. There are hundreds of examples. First of all, you could take any graph and make those dynamics, but okay, so that's the simplest hyperplane walks. Here's the next example, the braid arrangement. The braid arrangement, a famous arrangement, it's in RD, and the hyperplane Hij is the set of all x contained in Rd such that xi is equal to xj. So whatever else it is, it's a codimension 1 subspace. These aren't affine, they're actual hyperplanes, and they're, you know, the size of the number of hyperplanes is d choose 2. Those are the hyperplanes. So that's and you know, you could in 2 dimensions, you know, we all know, you know, x is less than y, x is bigger than y. These are familiar things. So what are the chambers? The chambers. So a point is in a chamber. Well, it's not on any of the hyperplanes. That means that none of its coordinates are equal. That means that the relative order is fixed throughout that chamber. So you can label the chambers by permutations. Finally, permutations, right? So the chambers are indexed by permutations. So there's n factorial chambers. You draw a picture in 3D, you know, and so there are the size of the set of chambers is n factorial, because no coordinates are equal. So throughout that region, there's a relative order, and you can just label the chambers by permutations. So you have to think for an hour, okay, but I don't have an hour to let you think. The faces, so you're on certain hyperplanes, that is, some coordinates are equal, right? And then you're on one side or another of other hyperplanes. That's our general definition of face. So how does that play out? They're indexed by block-ordered partitions. Ordered set partitions. So lambda is equal to lambda 1, 3, 5, 2, 4, 6, for example. So it's a partition of 1 up to d into disjoint blocks. So it's a set partition, but the blocks are ordered. And what it means is coordinates 1 and 3 are equal, and 3 and 5 are equal, but all of those numbers are less than all of the numbers in this block. And this block is parts of Rd which have a coordinate 2 and 4 equal, and labeled something. These are points in Euclidean space, and all of those should be bigger than these numbers. And coordinate 6 are points which are different than these and bigger than everything else. So but we'll have a picture and some stories in a second, but the faces are indexed by what are called block-ordered set partitions. And so what's the projection of a chamber on a face of a chamber on a face? So I think it's clear if I explain it, and writing it down is annoying, but I'll do the best I can. So I'm at a chamber. That's a permutation, which for me is an arrangement of a deck of cards. Okay. And there's this face, which is, say, this face, 1, 3, 5, and 2, 4, and 6. Okay, maybe it's some face. So find cards labeled 1, 3, and 5, wherever they are in the permutation. There they are. They don't have to be in order, you know, the permutation is whatever it is. But find cards labeled 1, 3, and 5. Okay, there they are. Take them out. Okay, and then find cards labeled 2 and 4. Take them out and put them under, and then take the last card and put it under. Okay. So at least I told you what it is, and I think you can understand, you know, how you do it. So it's sort of, well, it is exactly inverse shuffling. So let me, I'm going to say that, but so again, the projection of a chamber on a face is a permutation, and it's the permutation gotten by using the face as instructions as to how to inverse shuffle. Take the labels in the first block and put them here, and the labels in the second block and put them underneath, and the labels in the next block, put them underneath, and that gets you a different permutation. Okay, so that's a little lemma, but okay. So let me specify, so now I have to say something about face weights, and so let me give you the simplest example, which is the Zetlin library. So Zetlin is the Zetlin of Gelfand Zetlin. I mean, he was a wonderful Russian mathematician, Lie theorist, but being Jewish is not so easy when you were in Russia and in those days, and so he worked in a library sciences institute, and he did math, and this is one of the problems he invented. He was a smart guy. So I'll say it in this language. So let W sub f, if f is block-ordered set partition, be equal to Wi if f is a face with 2 blocks, one of which is a singleton, I d minus I. So it's a face with 2 blocks, one of which is the singleton I, and the second block is its complement, okay? And 0 otherwise, where Wi are now positive, and summation of Wi is equal to 1 up to d. So what does the Markov chain become on permutation? Information in manila folders. And imagine that you had a pile of manila folders, big pile, you know, as we all do, as the old ones do anyway, probably many young ones too. And you, you know, you say, oh, I have to find Huang, you know, where's his stuff? Down there, go, and I take it out. And then what do? Do I put it back in? Well, maybe I'm going to use it again. And so I put it back on top. I mean, I could do lots of things. I could try to put it back on top. I could move it up by 1. But this is an absolutely basic, the most widely used algorithm in what's called dynamic storage allocation, not for file folders in Persi, but for big tapes. If this storage, and when you call for a tape, and you have to go to the warehouse or something like that. It gets, and you do what you want with it. And should you put it back where it came from, or should you put it where it's more accessible? And it's what they do. They put it where it's more accessible. So this idea of move to the top, so with the chance of picking the ith folder or the ith card according to its popularity. Certain people, like I'm going to be looking at lots of long things, so I should keep it near the top. Okay, so at least I try to motivate. That's a non-symmetric Markov chain on the permutation group. I have weights W1 up to Wn, and I each time I pick a card out with probability, picking label I, and I move it to the top. And now, so that's called the settling library, and we're going to see what the stationary distribution of that is. So suppose I do it a lot. So cards with big weights are likely to be, it's not uniform, right? Cards with big weights are going to be on top, right? Or near the top, right? Okay, so that's an example of these geometric things. Another example is the different choice of face weights is let WF be equal to 1 over 2 to the D if the face F is equal to a set S and its complement. So there are, okay, so S is a subset of D. And 0 otherwise. So that's a choice of face weights. I just made them. And what is that Markov chain? Okay, let's just think about that. Here's a deck of cards. See, I've got you shuffling. And flip a fair coin for each card. And there are heads someplace. Call that set S. Take them out and put it on top. That's the Markov chain. That's exactly this Markov chain. What is that Markov chain? It's exactly inverse shuffling. Shuffling is this. Inverse shuffling is that. You take, pick the inverse of the permutation with the same weights, right? But remember, binomial. Remember the Gilbert, Chen, and Reed's model I was talking about the last 2 lectures, anyway. But so. That's the shuffling measure, the Gilbert, Chen, and Reed's measure is a probability distribution on the symmetric group. If you compose it with the inverse map, that's this, and repeatedly. So it's taking some cards out and taking some more cards out. That's the Gilbert. So this is shuffling, and the rate of convergence of inverse shuffling to random is the same as this is shuffling. See, I told you there was going to be shuffling. But actually, the projection, the projection of a chamber on a face, it is just shuffling. I take out the cards in the first block, and I remove them, and then I put the next block next, and it's inverse shuffling. Okay, so those are some examples, and more are coming. But So where are we? We defined hyperplane arrangements, and we defined a Markov chain by a choice of face weights. And so far, I haven't put any conditions on anything. And the claim is that there's a general theory for all of these, and it's gorgeous. So I have to convince you with it. But, so let me tell you some general theory that applies to all of these chains at once. So where I start is I have A, a hyperplane arrangement, C, the set of chambers, F, the set of faces, and some face weights. And so for arbitrary collection of affine hyperplanes, any number, they define chambers and faces, and then any face weights. Well, okay, I better do something about the any face weights, because you could always just pick one. So here's a definition. A set of face weights is separating if they're not all contained in the same hyperplane, if for every I there exists an F such that F is not contained in H sub I. So that just means the faces that are getting positive mass aren't all contained in the same hyperplane. And if they are, then just restrict attention to that hyperplane and get on with what you're doing. But that's the definition of separating. Okay, so here is the theorem 1. This Markov chain K of CC prime that I defined with these face weights, and still they're arbitrary, has a unique stationary distribution. So you keep shuffling, you converge to a well-defined limit. If and only if the face weights are separating. And okay, so it's a mild condition, and then there's a well-defined limit. The next theorem is so these matrices, this is a matrix. KCC prime is a matrix. They're not at all symmetric. Top to random, or sorry, random to top. Sorry, random to top. That's not a symmetric operator, right? It's not self-adjoint. It's not reversible. Riffle shuffling isn't. It's the inverse. If I pick the shuffle or its inverse with probability half, that would be reversible. But just shuffling, that's not symmetric operator. Yet these matrices have all real eigenvalues, and they're all positive, and they're easy to describe. So let's. In order to describe that, I need to tell you the intersection lattice. The L, the intersection lattice, of an arrangement, it's just all possible intersections of hyperplanes. So these are general hyperplanes in RD, and so hyperplanes are in the intersection. The intersection of two hyperplanes is in the intersection lattice. All possible intersections of all the hyperplanes. That's called the intersection lattice. It's a distributive lattice. The intersection lattice of A is all possible intersections. Possible intersections. Of H contained in A. And now I can say theorem 2, which is this Markov chain. It's not at all obvious. It's really not obvious. It's one of the theorems that I proved that is diagonalizable. This matrix is diagonalizable. With eigenvalues indexed by L, contained in L. So for every possible intersection of hyperplanes, there's a well-defined eigenvalue, and here's what it is. Lambda sub L is the sum of the face weights F, where F is contained in L. L is some intersection of hyperplanes. Look at all of the faces that have positive mass that are in that intersection, and add up those faces, and those are the eigenvalues. So they're positive and non-negative anyway, and this pretty explicit formula. And they have multiplicity. The multiplicity of lambda sub L is the mu of L and the top. The intersection lattice is a lattice, and so it's a partially ordered set inclusion, and the top thing is the empty intersection, or RD. The top thing is RD, and partially ordered sets have Möbius functions, and if you never saw that before, do something about it. Okay, I'm not going to try to fix that right now, but this is the notion of a Möbius function of a partially ordered set, and so if you look at the Möbius function of L to the top, that's a number, an integer, maybe sign, but take its absolute value. That's the multiplicity. And theorem 3 is sharp rates of convergence. So again, everything as above, the distance of k started at c after, say, m steps to stationarity. So there's this Markov chain, starts someplace, and I defined this the last time. This is the total variation distance after walking around m steps. How close am I to stationarity? It's less than or equal to the sum of h contained in A of lambda sub h to the nth power. So you can actually refine that, but this is most usually very good. So that is, h is one of the hyperplanes in the intersection lattice, and you look at lambda sub h is the sum of all face weights, where the face is a subface of h. And you raise that to the nth power. Those numbers are less than 1, and that's a reasonably sharp bound. I mean, I'll do examples, but it's a reasonably sharp bound. So I find that surprising and wonderful that in this generality, for this huge class of Markov chains, any hyperplane arrangement, any face weights, there's a unified theory this Markov chain, and it's had lots of ramifications, but even when applied to examples, it's useful and interesting. So the last thing I want to tell you about a little bit about this particular part of the subject is the stationary distribution. So that is the left eigenvector with eigenvalue 1. Theorem 1 says it exists, but it's not so good. I mean, it's better than nothing. But, you know, for example, weighted random to top, the Cetlin library, so you know it's some non-uniform distribution on the symmetric group. What is it? Can you write it down? And so let me say some things about that. The first thing to say is that if there's a group G acts transitively on the everything on the arrangement, acts transitively on the face weights on the arrangement, say, if there's a group that acts transitively, then the stationary distribution is uniform. And pi of c is equal to 1 over c. And so, for example, riffle shuffles or the Ehrenfest urn, everything's symmetric, and the stationary distribution is uniform. Of course, if you shuffle cards a lot, they get all mixed up. And okay, so that's a case. B, it'll be helpful for the general case. Let's do the Cetlin library. So remember, the Cetlin library is each card has a weight, and then each time you pick a card with probability proportional to its weight and move that to the top. And so, okay. The pi of sigma, where sigma is a permutation, I'll explain it and I'll write it down, but pi of sigma is sampling without replacement. From an urn with 1 up to n. So let me explain that. So put the weights W1 up to Wn in an urn. Okay, shake the urn up and remove one of the weights with probability proportional to its size. Suppose you remove 7. Okay, there it is. You took it out. And now you have n-1 weights left. Remove another weight from the n-1 with probability proportional to its weight relative to what's there, 15. Okay, keep going. You're generating a permutation, right? And the first one is likely to be one of the big weights. So is that okay with anybody? Okay, everybody. Okay. So you can write it down. This is equal to W of sigma 1 times W of sigma 2 over 1 minus W of sigma 1 times W of sigma 3, the chance of getting Jesse. More applause for Jesse. Right? So you know, sometimes you can write down the stationary distribution. So let's do the general case. See, in general. So I'm now just in complete generality. I have an arbitrary hyperplane arrangement, arbitrary phase weights. Suppose they're separating. I mean, so that there is a stationary distribution, say separating. Separating. Here's a description of the stationary distribution. Pi of C has the following description, is described as I'll say it in steps. Put all the face weights, all of them, in an urn. Okay, and remove them one at a time, all of them, with probability each time removing one of the face weights with probability proportional to its size relative to what's left. So sample without replacement. So they come out in some order. It's now random what comes out, right? But generating, say, the first one that you picked out was F1, then F2, and then F sub the size of F. So pull the face weights from the urn that way, and then take any chamber, or any C naught, doesn't matter, form C naught and multiply it by the last thing you picked times F subscript F. And then the next to the last thing, remember, you can multiply a face by a chamber and you get a chamber, and then multiply by F subscript F minus 1, and keep going and finally multiply by F1. So multiply by the chambers, by the faces in the order, inverse order to which you pick them. That's C. So this is an algorithm for perfectly sampling from the stationary distribution. And you can write it down as a formula, but it doesn't help. I mean, it's a messy formula. You know, it's pi of C is the sum over all possible orders. I mean, you can write it down as a formula, but that doesn't help. But that's a big step. So it's like the Cetlin library, but with some bells and whistles. I want to say, so I'm not going to do any more examples. There is a handout, and if you look at the handout, you'll see there are references, and but I want to at least say this. So, you know, I just took you through some stuff about hyperplane arrangements and Markov chains. So who cares about hyperplanes? Probably nobody in this room cares about hyperplane. Anybody in this room hyperplanes? And you? Oh, bless you. Okay, so sometimes, so you can ask her about why is it interesting. So who cares about, but most mathematicians don't know about hyperplane arrangements. Is that, you disagree? Okay, who cares about hyperplanes? We can discuss. Good. The main people that care are people in algebraic geometry and topology, where if you have a set of real hyperplanes, and if you look at them in complex space, then the complement of the set of real hyperplanes in complex space is a topological space. It's not so easy to picture, and for example, Deline and Briskov showed that if your arrangements are the arrangements of a finite reflection group, those pi1, those hyperplane complements are k pi1s. They're Eilenberg-MacLane spaces. The first homology is the group, and then everything else is zero. And so they're a big deal in parts of algebraic geometry. And there's a beautiful book, if you like stuff like that, by Orlik and Solomon, or is it Orlik and Terau? Orlik. I know, Terau maybe. On hyperplane arrangements from that point of view, and that's one place. That's one place they come up. There's a modern place they come up, and if you are a young mathematician who likes abstract math, you won't have seen any in this talk. In this set of talks, but I'm not opposed to it or hostile to it either. So I have two friends, Marcelo Aguiar and Swapnil Mahajan, who have written 3-4 huge books, which take this math I just did, all of the math I just did, and they apply it to the most marvelous generalization of algebra. So, as many people know, G finite group is a finite reflection group. Well, it's generated by reflections generated by SI with relations SI squared is 1 and SI Sj to the Mij some numbers is 1. So the finite reflection groups, Coxeter groups, are classified, these all possible finite groups which are generated by reflections and have this kind of relationship structure. And for example, the symmetric group, Sn, is generated by the adjacent transpositions, and Mij is equal to, 2 if I and j are bigger than 2, if the two transpositions disjoint, and is equal to 3, I guess, because this is a 3 cycle, if I minus j is equal to 1, if I got it right. And so these are called type A, and what Aguiar and Mahajan did is they made analogs of all the basic notions of algebra, associative, commutative, Lie, Hopf, lots of basic constructions of algebra, but they abstracted them so that you can define Lie algebras and Hopf algebras and associative algebras for general hyperplane, associated to general hyperplane arrangements. And it's not crazy or baloney, it's just great math. And all kinds of math that has been done, for type A, now applies very generally. And so I put the references to their 4 volumes, but if you're interested in modern math, and if you follow this talk enough so that you have a feeling for what the Tits projection is, that's really all you need, and what a hyperplane arrangement is, you can start to read one of their books. And it's just, I promise you, it's wonderful, wonderful math. I'm going to stop because I am already over, and but I hope one thing that you got out of this, so the subject I've been talking to you about, I think of as applied probability or probabilistic combinatorics or I don't know what to call it. So if you've just seen 3 lectures in that kind of subject, and it's healthy, it's live, it's full of interesting, lively problems. And if I can help you find one, I'm here all next week. And if you want to tell me about something that you do that sounds related, in particular, if you know about hyperplane arrangements, I like hyperplane arrangements. Please come and say hello. Thanks. See you.
Thank you, Persi, for this set of wonderful lectures. Are there any questions or comments? Okay, if not.